Hi guys, today we're going to talk about definite integrals, and we're also going to combine that with the fundamental theorem of calculus today. This is going to be a long lesson, so you need to stay with me. You might need to play different parts of this at different times. So, definite integrals. So up to this point, we've looked at things that look like this. The integral of 2x dx, and we figured out that that was x squared plus c. Okay? Well, now we're going to look at, that's an indefinite integral because there's no borders on this. So with a definite integral, we're going to add something like this. We're going to add something like from 0 to 4. Okay, so what that's going to do is that's going to find the area under the line y equals 2x. So 2x would look something like this. We're going to find that from 0, 2, 3, 4. Okay, so we're going to find the area of this under here. So we have borders on this thing. We got 0 on this end and we got 4 on this end. Okay, so first of all, we need to know that continuity implies integrability. So if f is a function and it's continuous on a closed interval ab, then I can integrate it on ab. That is, and we read this as the integral from a to b of f of x dx exists. So let's look at one. Let's look at this one. Evaluate the definite integral from -2 to 1 of 2x dx. Okay, so the first thing we're going to do is, let's rewrite this so it's a little easier to read. Here's my integral. I'm going to integrate that thing, and I'm just going to look at this part right here for now. The integral of 2x, probably already know, is x squared. And instead of adding a plus c, we're going to evaluate it from -2 to 1. Okay, now how do we evaluate it? Well, here's the way you evaluate it. You take f of b and you subtract f of a. Notice those are capitals. So this is the integral of the function, so that's x squared of b. This is b, and then this is a. And so we just plug those numbers in and we subtract. So in this case, this would be 1 squared minus -2 squared. Okay, which would be 1 minus 4, which is -3. Now, we know an integral is an area. How do we get an area of -3? Well, essentially it's this. We're integrating, we're finding the area under the curve 2x, okay? So, let's see. We're going from here. So 2x would be 2 right here, and -2 squared would be -4 would be right here. So here's my curve, and what I'm doing is I'm finding this area, and I'm subtracting that area. Anything below the curve is going to be negative, and anything above the curve is going to be positive, okay, or above the x-axis, I mean. So this area right here is going to be 1, and this area is going to be -4. When I add those together, I get -3 for my area. Okay, the definite integral as the area of a region. If f is continuous and non-negative on the closed interval ab, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is area equals the integral from a to b of f of x dx. Okay, so just to kind of have a picture, okay, here's my f of x, something like this. All right, and here's A, this would be f of A, and here's f of B, and here's B. Okay, then what I'm finding is I'm finding the area between A and B above the x-axis and under the curve. So I'm finding this area right there. so let's look at a couple of these. We're gonna find the integral from 1 to 3 of 4 dx. Okay, so if I integrate the 4, I'm going to get 4x evaluated from 1 to 3. I don't add c to these. So now I'm going to take 3 and plug it in there. I get 4 times 3 minus 4 times 1, which is 12 minus 4, which is 8. So I've evaluated my function. The area under the curve from 1 to 3 of 4 is 8. Now, I can look at this geometrically if I want. 4 is just a horizontal line, okay, at 4. So here's my graph. I'm going from 1 to 3 of the line which is 4. Now the line that's 4 is just this line right here. It's a horizontal line, okay, and I'm finding the area from here to here. So basically, I'm finding the area of this rectangle right here. Well, there's 2. That's 2 across the bottom. That's 4 up here. So the area of a rectangle is 4 times 2, which is 8, which is what I got right there. Okay, the integral from 0 to 3 of x plus 2 dx. All right, so I'm going to integrate this. 1/2 x squared plus 2x evaluated from 0 to 3. So first I'm going to plug in 3. So I'm going to get 1/2 of 3 squared plus 2 times 3 minus, now I'm going to plug in 0, so I'm going to get 1/2 of 0 squared plus 2 times 0. Okay, well obviously this is just 0 here. This is 6. And this is 9 halves, so that's 4.5. Okay, and then I just add that up and I get 10.5. There you go. Now I could figure this out if I wanted to graph, if I wanted to do it geometrically. Okay, and I graph the line x plus 2. So 1, 2, and I'm going from 0 to 3, so 1, 2, 3. So this is going to have a slope of 1. So it's going to, the line's going to cross right here. Okay, and it's going to rise 1 and run 1, so it's going to end up right here. Oops, I missed. So I'm just finding the area so I'm finding this area right here. That's a trapezoid. It's got a base here of 2 and a base here of 5, and it's got a height of 3. Well, if I think back to my formulas, the area of a trapezoid is 1/2 the height times base 1 plus base 2. Okay, so base 1 is 2 and base 2 is 5, and the height is 3, and I want half of that. So this would be 3 times 7, and I want half of that, and that's 21. Half of 21 happens to be 10.5. Look at that. The area matches my integral. Okay, the integral from -2 to +2 of the square root of 4x squared. Okay. So this one, let's rewrite this as 4 minus x squared to the 1/2. Okay. Now that one I haven't given you a technique for yet to integrate this. So I'm going to go ahead and skip this one at this point. Right here. We could do this geometrically because this is what happens when you cannibalize one lesson with another one. So this is a semicircle. So it's going to go from -2 here to +2 here, and it's going to be finding the area under that curve right there. So this is a circle with a radius of 2. Remember, a circle is area pi r squared, and so I just plug in 2. And area is going to be 4 pi. Okay, so we'll get a technique for integrating that just a little bit later. Oh wait, I forgot to take half of that because it's a semicircle. Sorry about that. So we need to take half of all that. So the area is actually going to be 2 pi. Okay. So definitions of two special definite integrals. If f is defined at x equals a, then the integral from a to a of f of x dx is 0. So if you think about that, it makes sense. You're basically saying, I've got this graph, and I've got this point A on the graph, and here's some curve, and I want the area from A to A. So I want the area between A and A. It's just a vertical line. It has a width of 0. And so the base is 0 times whatever the height is going to be 0. So the area is going to be 0. If f is integrable on a to b, then the integral from b to a of f of x dx equals the negative integral from a to b of f of x dx. Okay, that comes in handy sometimes, where you can switch this thing around and just take the negative. Okay, so this would be something like the integral from 4 to 2 of f of x dx would just be negative the integral from 2 to 4 f of x dx. Okay. So evaluate these. So find the integral from pi to pi of sine x. Okay, that's just 0. You're going from pi to pi. There's nowhere to go. Okay, the integral from 3 to 0 of x squared plus 2 dx, well, that's equal to the negative integral from 0 to 3 of x plus 2 dx. So let's integrate both of those and take a look at how that works. So if I integrate this, this is going to be 1/2 x squared plus 2x evaluated from 3 to 0. And over here, this would be negative, oops, take the integral. So this is going to be negative 1/2 x squared plus 2x evaluated from 0 to 3. Okay, so if I plug in 0, I'm going to get 0 plus 0. So this is 0 minus 1/2 of 3 squared plus 2 times 3. So this is 0 minus, this is 4.5 plus 6, which is negative 10.5. Okay, over here, this is going to be negative 1/2 of 3 squared plus 2 times 3 minus, if I plug in 0 there, I'm going to get 0. Okay, so this is negative 4.5 plus 6, which is negative 10.5 again. So you can see it works out. Okay, additive interval property. If f is integrable on the three closed intervals determined by a and b and c, then this is true. So the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. So essentially what that means is this. I've got some curve here, okay, and here's a, and here's b. So the integral from there to there has an area, and then it's saying, well, I got some point c somewhere in between here, and it's just saying, well, if I find the integral of this area, and then I add it to the area of this area, then that's the same as the integral from a to b. Okay, here we're going to use the additive interval property. So find the integral from negative 1 to positive 1 of the absolute value of x. So this is one that you kind of, if you look at the graph of it, it's very helpful. So absolute value of x from negative 1 to 1, it's going to look like this, right? So if you plug in negative 1, you're going to get out positive 1. If you plug in positive 1, you're going to get positive 1. So essentially what you're doing is you're finding the area of those two triangles. Okay, so what I can do is I can take this problem and I can find the integral from negative 1 to 0. Now, this is the curve negative x dx, and I can add that to the integral from 0 to 1. This curve is just x dx. Okay, so the absolute value of x is essentially two lines. This one is y equals negative x, and this one's positive x. So I can break that up and I can find this. Okay, so then the integral of this is going to be 1/2 x squared, evaluated from negative 1 to 0. I'm going to add to that, oops, this is negative 1/2 x squared. Sorry about that, forgot my negative sign. This one's going to be 1/2 x squared, evaluated from 0 to 1. Okay, so this is going to be negative 1/2 of 0 squared minus negative 1/2 of negative 1 squared plus 1/2 of 1 squared minus 1/2 of 0 squared. Okay, so this right here is going to be 0 plus, those two negatives cancel out, that's going to be 1, so this is half of 1, which is 1/2. Plus, over here I'm going to get 1 squared times 1/2 is 1/2 minus 0. And I end up with 1/2 plus 1/2, which is 1. Which makes sense with this picture. I mean, if you look at the triangle, remember the triangle is half the base times the height, so the base is 1 and the height is 1, and the base is 1 and the height is 1. So 1 times 1 is 1, take half of that, that's 1/2. This triangle has an area of 1/2, that triangle has an area of 1/2. Add them together, I get 1. Okay, properties of definite integrals. So if f and g are integrable on the interval a to b, and k is a constant, then the functions k times f and f plus or minus g are also integrable on that same interval, and the integral from a to b of k f of x dx is just k times the integral from a to b of f of x dx. So essentially what that means is, if I had something like this, integral from 0 to 4 of 2x dx, I could just change this to 2 times the integral from 0 to 4 of x dx. And then I could solve that. And down here, okay, basically if I've got a function that I'm adding together, I can break that apart and add the two parts. So if I had something like the integral from negative 2 to 4 of 3x squared minus 2x dx, I can take this and make this, I can break this apart, make this the integral from negative 2 to 4 of 3x squared dx minus the integral from negative 2 to 4 of 2x dx. And then if I wanted to, I could even take the constants out. Uh-oh. I could take the constants out and make this that if I wanted to. Now on this particular problem, this would be a lot more work to do this than to just integrate the whole thing. But there you go. Okay, evaluate this definite integral. From the integral from 1 to 3 of negative x squared plus 4x minus 3 dx. Okay, so we're going to integrate this. So this is going to be x cubed, I'm going to need a 1/3 here. And then that's going to be plus, this is going to be x squared, I'm going to need a 2 right there. Minus 3x. Okay, so I've integrated that. I'm going to evaluate it from 1 to 3. So to do that, I'm going to plug 3 in. I have negative 1/3 times 3 cubed plus 2 times 3 squared minus 3 times 3. I'm going to subtract that from that. Negative 1/3 times 1 cubed plus 2 times 1 squared minus 3 times 1. So this is going to be 27 times negative 3. That's going to be negative 9. This is going to be 9 times 2 is 18 minus 9 minus. Okay, this is going to be 1 times negative 1/3. It's going to be negative 1/3 plus that's going to be 2 minus 3. This is going to be 0 minus. Okay, so I'm going to have negative 1, negative 4/3. And so that's going to come out to be positive 4/3. So there's my area under that curve. Preservation of inequality. So if f is integrable and non-negative on the closed interval ab, then 0 is less than or equal to the integral from a to b of f of x dx. If f and g are integrable on the closed interval ab and f of x is less than g of x for every x in ab, then the integral of f of x must be less than the integral of g of x. So this kind of makes sense. I mean, if you think about it, what that means pictorially is if I've got f of x is always less than g of x on an interval, oops. So here's g of x, and here's f of x. So you can see f of x is always less than g of x on this interval. Then the area, the integral of f of x is going to be less than the area of the curve under the curve of g of x. Okay, I got about 5 or 6 problems I want you to do out of this lesson right here. Okay, just going to do 33 through 43, the odd ones, which that's none of those on that page, but there's some on this page. Okay, so you're going to do them over here. Find some integrals. And there's some reading for the, uh-oh, forgot to add the rest of those pages for reading. To go back and do that. So we're going to talk about the fundamental theorem of calculus now. Okay. Informally, the fundamental theorem of calculus says that differentiation and definite integration are inverse operations, just like multiplication and division are inverse operations. So the fundamental theorem of calculus. If a function f is continuous on the closed interval a, b, and capital F is the antiderivative of little f on the interval a, b, then the integral from a to b of f of x dx is capital F of b minus capital F of a, which is what we were just doing. So guidelines. Provided you can find an antiderivative of f, you now have a way to evaluate a definite integral without having to use the limit of a sum. So we don't have to do that limit stuff anymore, which is good because the limit stuff takes forever. It takes a lot of paper. It's difficult. I can use the fundamental theorem of calculus and I can find an integral pretty dang easy. 2, when applying the fundamental theorem of calculus, the notation shown below is convenient. So the integral from a to b of little f of x dx is capital F of x, which is equal to capital F of b minus capital F of a. Point 3, it's not necessary to include a constant of integration, c, in the antiderivative. Okay? And you can go through this to see why. I mean, if I take the integral of this, the integral of f of x is capital F of x plus c evaluated from b to a. So I would plug b in here. So this would be f of b plus c, right here, minus f of a plus c. But if I distribute this minus sign in here, I get f of b minus f of a, and then c minus c, the c's just cancel. So I don't need to do that. Okay, so this is going to cancel that. And I don't need the integration constant. Okay, let's evaluate these. So the integral from 1 to 2 of x squared plus 3, or x squared minus 3, sorry. So the first one here, I integrate that. You know what? Pause the video right here, integrate this, then come back and compare it to what I got. Okay, so if we integrate this, this is going to be 1/3 x cubed minus 3x evaluated from 1 to 2. So first I'm going to plug in 2. It's going to be 1/3 of 2 cubed minus 3 times 2 minus, then I'm going to plug in the 1. 1/3 of 1 cubed minus 3 times 1. Okay, this is 8/3. I really don't like that. This is 8/3 minus 6 minus 1/3 minus 3. Okay, in thirds, this is 18/3, so this is negative 10/3 minus In thirds, this would be 9/3, so this would be negative 8/3 right there. And of course, those two things are going to cancel out, and I'm going to get negative 2/3. Okay, next up. The next equation here, the integral from 1 to 4 of 3 times the square root of x. So I'm going to rewrite this as the integral from 1 to 4 of 3x to the 1/2 dx. Okay, so if I integrate this, I'm going to get 3/2 for the power, which means I'm going to need a 2 down here, because 3/2 times 2 is 3. I'm going to evaluate that from 1 to 4. So that's going to be 2 times 4 to the 3/2 minus 2 times 1 to the 3/2. Guess I don't need this bracket out here. Okay, so let's see. This means the square root of 4 to the 3rd power. So that's going to be 2 to the 3rd power is 8 times 2 is 16. 1 to the 3/2 is 1, so 1 times 2 is 2, so it's going to end up being 14. Okay, last one. So the integral from 0 to pi over 4 of secant squared x dx. So we integrate this, and the integral of secant squared is tangent x evaluated from 0 to pi over 4. So this is going to be tangent of pi over 4 minus tangent of 0. Okay, tangent pi over 4 is just 1. So this is 1 minus tangent of 0 is 0. This comes out to be 1. All right, let's do an absolute value. So this is one where you want to break it apart. So I always like to make a quick sketch on a graph. Here's the absolute value of 2x minus 1. Okay, on this side, it's going to be 2x minus 1, and on this side, it's going to be negative 2x plus 1. So what I'm going to do is I'm going to break this apart. It changes at 1/2, because that's where this thing is 0, and it's where the vertex is. Okay, so I'm going to make this the integral from 0 to 2 of the absolute value of 2x minus 1 dx is going to equal the integral from 0 to 1/2 of negative 2x plus 1 dx plus the integral from 1/2 to 2 of 2x minus 1 dx. All right, so let's integrate these things. So this is going to be x squared. I need a negative out here, plus x, evaluated from 0 to 1/2. This is going to be x squared minus x, evaluated from 1/2 to 2. Go ahead and plug in the 1/2. I don't have to do the 0, because 0, if I plug it in there, is just going to be 0. So this is going to be negative 1/2 squared plus 1/2 minus 0. We'll just put that in. Okay? Plus, now this one's going to be a little different. This is going to be 2 squared minus 2 minus 1/2 squared minus 1/2. And it's minus all that. Okay. So this is going to be 1/4, negative 1/4 plus 1/2 is going to be positive 1/4 plus, so 2 squared is 4, minus 2 is 2, minus, that's going to be 1/4 minus 1/2. This is going to be negative 1/4, but this is going to cancel that out, so it's going to be 2 plus 1/4. Plus 1/4. So this is going to end up being 2.5. Now I could check that using the graph. I mean, this is definitely 1/2 right there. And then this right here is going to be, I got kind of a goofy graph here because this is not to scale x's and y's. So, oh wait, I'm sorry, that's not 1/2. That's 1/4 because my base is 1/2 and my height is 1. So it's going to be half the base. Oops. Times the height. And then I'm going to add to that this over here, which is going to be a triangle. It's half the base is going to be 3/2. And the height is going to be, let's see, if I put 2 in here, I'm going to get 3. That's going to be 3. So this is 1/4 plus, this is going to be 3/4 times 3, which is 9/4. So this is going to end up being 10/4, which is 2.5. So it matches. I can do it geometrically, I can do it with calculus. All right, let's talk about the mean value theorem here. Okay, if f is continuous on a closed interval AB, then there exists a number c in the closed interval AB such that the integral from a to b of f of x dx is equal to f of c times b minus a. All right, so if you think about this, this is what it's saying. I've got this curve that goes like this, okay, and it goes from a to b, and they're saying somewhere in here is a c, all right, where f of c, there's f of c right there, times b minus a is the same as the area. So this is the area under this curve, under the red curve right here, from a to b. Now, if I look at that, this rectangle has a base of b minus a, that's where that comes from, the base of the rectangle, and f of c is the height. So what they're saying is you can come in here, find a c where you could draw this line across here, take anything above this and move it down into here. Take anything above here, move it down into here, and I just find the area of a rectangle. And it's the mean value of all these values right here. Okay, so find the value of c when f of x equals the square root of x on the interval from 4 to 9. Okay, so that's going to say that the integral from 4 to 9 of x to the 1/2 dx is going to equal some f of c times b minus a, but b is 9 and a is 4. Okay, so I can integrate this. That's going to be that, evaluated from 4 to 9. And this is going to equal 5 times f of c. So then this is going to be 2/3 of 9 to the 3/2 minus 2/3 of 4 to the 3/2. And that's going to equal 5 times f of c. So this is the square root of 9 is 3, and 3 cubed is 27. So this is 50. This is 54 thirds minus the square root of 4 is 2, cubed is 8. So this is 16 thirds equals 5 times f of c. So let's see, 44, 38. This is 38 over 3 equals 5 times f of c. And now I divide both sides by 5, so this would be 38/15 equals f of c. Which is what, 2... Change that to a decimal there. Okay, anyway, we can find, okay, so now we know that f of c is 38/15. So the square root, I don't like that number, let's change that to a decimal, 38/15. 2.53 repeating. So f of c is 2.53 repeating. Now, I was supposed to find c. So I'm trying to find this point right here. I found this point. I'm trying to find this point. So if f of c is 2.53, then the square root of x, okay, that's f of c, is 2.53 repeating. So I'm just going to square this. So x is 6.417 repeating. Or I should say c. Let's just do this. All right, where was I? C. Okay, there you go. All right. Average value of a function. So the value f of c given in the mean value theorem for integrals is called the average value of f on the interval ab. So the definition is if f is integrable on the closed interval a to b, then the average value of f on the interval is 1 over b minus a. Bar didn't go all the way across here. 1 over b minus a times the integral from a to b of f of x dx. Okay, so if you look at it, here was our mean value theorem, okay? B minus a times f of c equals this integral. So if I just divide this over here, okay, that's the same as 1 over b minus a, that's this, times that equals f of c. Okay, find the area under the region bounded by the graph y equals 2x squared minus 3x plus 2. Okay, so we're going to find the integral from 0 to 2, because that's my vertical lines. Okay, here's 0, here's 2. Okay, of this function. So that's easy to integrate. There it is. So bump it up to a cube, I need 2/3 out here. Bump it up to a square, I need 3/2. Make that 2x, evaluate it from 0 to 2. Plug in 2, that's this. If I plug in 0 on all this, I just get 0, so I just subtracted the 0 there. Okay, you should be able to do this algebraically easy enough. This ends up being 16/3 minus 6 plus 4, which is 3 1/3. Okay. That's my area under the curve. You can kind of estimate that too, looking here. I mean, here's 1 and here's 1. This is not the scale on the x and y's, but that's about 1. That's about 1. This is about 1. There's a little bit left over. Okay, find the average value of a function. Find the average value of f of x equals 3x squared minus 2x on the interval from 1 to 4. Okay, so I'm going to use my formula. It's going to be 1 over 4 minus 1, so that's my 4 minus 1, times the integral from 1 to 4 of that, 3x squared minus 2x dx. Okay, if I integrate this is just x cubed minus x squared. This becomes 1/3 out here, and I'm evaluating from 1 to 4. So I plug in 4, and I subtract plugging in 1. This ends up being 64 minus 16 minus 0. I want 1/3 of that. So it's 1/3 of 48, which is a nice number. That's 16. So there's my average value. Okay, this problem has a lot of busy work. So at different altitudes in Earth's atmosphere, sound travels at different speeds. The speed of sound, s of x, in meters per second, can be modeled by s of x equals negative 4x plus 341 when 0 is less than or equal to x is less than or equal to 11.5. 295 when x is between 11.5 and 22. 3/4 x plus 278.5 when x is between 22 and 32. 3x plus 254.5 when x is between 32 and 50, and negative 3x plus 405.5 when x is between 50 and 80, where x is the altitude in kilometers. What is the average speed of sound over the interval from 0 to 80? So here's the unfortunate part. I got to integrate all 5 of these and find their values, okay? So we take the first one, 4x plus negative 4x plus 341, and we integrate that from 0 to 11.5. Okay, this becomes negative 2x squared plus 341x, evaluated from 0 to 11.5. And you're going to take my word for it, that's 3,657. Next, we integrate 295. Well, that's 295x, evaluated from 11.5 to 22. That comes out to be 3,097.5. We evaluate this next. There it is. The integral from 22 to 32 of 3/4 x plus 278.5. So here's the integral, evaluated from 22 to 32. That comes out to 2,987.5. There's the next integral. And then the fifth one. So we've got these 5 values here. Okay? And we're going to take those 5 values, we're going to add them all up. And we're going to divide it by 80. So it's about 308 meters per second. And that checks out with our answer. Okay. So here's the assignment that I'm going to give you for 4-4. So you're going to have 2 pieces of the assignment. You got these problems for this lesson, and you got 5 other problems for the previous lesson. So there you go. I will see you next class, and I will answer any questions you got from your homework.